Today we will discuss the gauge symmetry, which is the way of understanding the interactions of particles. As we go on, it will be clear what we mean by that. So far we have been discussing the interactions of particles through their equations of motion, and we did motivate the Dirac equation, how it arises, and also the Klein-Gordon equation, and then basically use the perturbative technique to compute the cross section. We went on to describe the weak interaction also along the line of the electromagnetic interactions, and now we will try to see how everything can be understood from a symmetry point of view, or which then can be taken as the basic principle, guiding principle, and things can be built from these guiding principles. For that, we will start with what is called the Lagrangian of the system. So, the basic thing here is the fundamental thing is the Lagrangian of the system, and the equations of motion can be derived from the Lagrangian. For point particles, a discrete system of point particles, we can talk about the Lagrangian as for many cases it is the kinetic energy minus the potential energy. So, T here is the kinetic energy and V is the potential energy. For example, free particle, kinetic energy is half mass of the particle times the velocity square. If I consider for simplicity one dimensional system, particle moving in one dimension, then its velocity is the position coordinate, time derivative of the position coordinate, and kinetic energy is half m x dot square, and potential energy for a free particle is 0. That gives us the Lagrangian equal to half m x dot square. Sorry. Now, without deriving, we will describe what is the equation of motion. In this case, you take the derivative of the Lagrangian with respect to x dot, and that will give you derivative with respect to x dot of half m x dot square, which is equal to m x dot. Now, you take the time derivative of this, that is x double dot, and equation of motion for any Lagrangian with one such coordinates is time derivative of the Lagrangian with respect to velocity minus derivative of the Lagrangian with respect to the coordinate itself is equal to 0. That is the equation of motion, which is called Euler-Lagrange equation of motion. So, this gives us in our present case x double dot equal to 0, which is the statement that acceleration of the particle which is freely moving is equal to 0, that it will move with constant speed. So, this particular Euler Lagrangian equation can be generalized to more than one coordinates, and in particular we are interested in continuous system of particles. For continuous system of particles, continuous system, say a block of matter, solid block or things like that, we have infinitely many degrees of freedom. So, there are infinitely many particles, very large number of particles. So, infinitely many in loosely speaking, and this can be then considered as, or the position of the particular point. Okay, so, we can assign some kind of a function which describes the configuration of the system at a particular time in that way. So, for that actually we rely on we will define some function which is a function of the spatial coordinates and the time coordinates, or in general we can write it as a function of the 4 vector. Okay. And we can consider the Lagrangian now as a function of, instead of the coordinates and the velocities, in the case like in the case of the particle mechanics, we can now consider it as function as a function of these phi's, which are the functions of the coordinates, and the derivatives, spatial and time derivative of this, and it can also depend explicitly on the spatial coordinate. And this is basically what we will consider to start with is the Lagrangian density in this case. And actual Lagrangian is obtained by integrating this Lagrangian density over a volume, over the volume of the system. And the equations of motion generalize to derivative of the Lagrangian density with respect to the dou phi or dou mu phi and take the derivative of this whole thing minus derivative of the Lagrangian density with respect to phi equal to 0. Again, we are not going to prove this, we are not going to derive this, we are not going to discuss anything more about how this equation is arrived at. But one can actually look at any standard classical mechanics book, including Goldstein's classical mechanics by Goldstein, or any other field theory, classical field theory book, then or quantum field theory book, where introduction to classical field theory is given, to understand what is the Lagrangian mechanics and how do you get the equations of motion in Lagrangian mechanics. Now, we will but illustrate this in our situations. So, let us consider a particular Lagrangian density. I will write it as 1 over 2 dou mu phi minus m square over 2 phi square for some field phi. some function of x mu, phi is some function of x mu. So, in that case I can write dou L by dou phi, I will get it as m square phi and dou L over dou derivative with respect to dou mu phi. How do I write it? Second term there is no dou mu, but the first term has. So, what I will do is to write it in a more convenient way. It is, there is a factor of 1 over 2 there, and I will write it as dou alpha phi dou alpha phi, so that there is no confusion with the mu that we are taking. Alpha is a dummy index and mu written in the Lagrangian density is a dummy index. So, I can write it in this fashion. So, half derivative with respect to dou mu phi of, now since I am taking derivative with respect to a covariant derivative of phi, I will write everything in the square bracket here in terms of the covariant derivative. I can do that by using G mu nu or G alpha beta or the metric tensor G. So, I will write it as G alpha phi as it is, and this one is G alpha beta dou beta phi. I hope everybody understands the operation that we are doing. G alpha beta is a metric which is independent of space time coordinates for special theory of relativity. So, we will take that out. In our formalism, we do not have any space time dependence for the metric. Okay, so, then we have dou alpha phi dou beta phi. What is this? Derivative with respect to mu dou mu phi of dou alpha phi dou beta phi. I have just rewritten this thing here, is equal to first take the derivative. I will go slow here, so that we understand the steps, and then we will go a little faster later on. First, let me take the derivative with respect of the first factor here, dou alpha phi, okay, and the other one is a spectator, plus do the other way around, dou alpha phi is a spectator and the derivative acts on dou beta phi, which is equal to, this two are the same as long as you have same index on both the one which you are differentiating and the one which you are differentiating with respect to. So, this essentially gives you a delta mu alpha, a Kronecker delta, which says that this is equal to 1 if mu is equal to alpha is equal to 0 otherwise. Dou beta phi plus similarly dou alpha phi delta mu beta. In case you get lost with the indices, what you have to check at every stage is that the number of free indices on either side and in all the terms are the same, and wherever you have a repeated index, that is summed over, and that you want that to be summed over. So, here for example, each of this term on the right hand side has a mu as a contravariant upper index and an alpha and a beta as the covariant indices for both the terms. and on the left hand side we have a covariant alpha and beta indeed, and a covariant mu in the denominator, which is equivalent to a contravariant mu in the numerator. So, that is fine. This is what you have. Look back at what you have in dou L derivative of L with respect to dou mu phi g alpha beta. So, let me write that down. Derivative of L with respect to dou mu phi is then equal to g alpha beta by 2 g alpha beta contravariant by 2 into whatever else that we have here in the this thing. So, that is delta mu alpha dou beta phi plus dou alpha phi delta mu beta. Taking all these contractions, now again there is only one free index, alpha, beta are dummy indices contracted, and on the left hand side we have only one free index. So, it all agrees. Now, let us put this g alpha beta and multiply the first term with that. What is happening is, it will okay, firstly the delta mu alpha will change the alpha to alpha in g alpha beta to mu. Okay, maybe let us do that slowly in the next slide. So, this therefore equal to okay, g alpha beta. I will use the delta function first to change mu to alpha, sorry, alpha to mu. So, I have a g mu beta over 2, this is only the first term, into dou beta phi. And for the second one, we have a delta beta mu. So, mu will be beta will be changed to mu. So, we have dou alpha phi as it is, g alpha beta, alpha mu, beta is changed to mu. Again by 2. So, this is equal to 1 over 2. The role of g mu beta acting on dou beta phi is to raise the index beta to mu, make it contravariant. So, we have first term dou mu phi, second term instead of beta you have an alpha, no other difference. So, it is dou mu phi, which is equal to dou mu phi without a half factor. That is it, all right. So, that is what you have here, and you have one part, this one, which will go into the equation of motion, and the other part here. Okay. So, that will give you equation of motion as derivative of dou mu phi minus m square phi. Sorry, actually there is a minus sign here already. So, it should be plus m square phi. This is equal to 0. What is this? This is the Klein-Gordon equation. So, summary is that if I use the Lagrangian density, half dou mu phi mu summed over minus m square by 2 phi square for a function phi, that will give us dou mu phi plus m square phi equal to 0. The Klein-Gordon equation. So, we can say that the Lagrangian that we have written down is the Klein-Gordon Lagrangian, or the Lagrangian corresponding to a Klein-Gordon field, or a field that satisfy, or a function that satisfy the Klein-Gordon equation. Okay. Now, these functions are called fields, and we can actually say that this represents or corresponds to a particle. So, this is field is the one which will represent a particle. So, this is what is the quantum field theory does. In relativistic quantum mechanics, when we discuss the Klein-Gordon equation, we considered the phi as wave function, and there is a subtle difference here when we actually consider this phi now as a field. Again, we will not go into the details of what is what. It can be taken as a kind of a technical difference here, but the bottom line for us today here is that we represent particles now by fields, or rather the fields acting on some vector space or the state vector, and corresponding to each different particles, we will have different fields representing them. So, one such field is this phi. There is a way to actually relate the spins of the particles to understand the spins of the particles also, and we will see that usually the scalar particles are the ones which are described by, or the spin 0 particles are the ones which are described by Klein-Gordon kind of Lagrangian that we have just now written down, which we are staring at. Now, another type of particle that we had encountered earlier is this Dirac, the ones which satisfy the Dirac equation, and in passing we had mentioned that this is basically the type of particles which are described by Dirac equation are spin half or fermionic particles, for example, electron. So, let us consider that kind of Lagrangian. Consider the Lagrangian I times psi bar gamma mu dou mu psi minus m psi bar psi. Okay. If you take this Lagrangian and then consider psi and psi bar as independent, degrees of freedom, independent wave functions. So, Lagrangian is a function of psi, psi bar and dou mu psi in this case. Now, let us look at the equation of motion with respect to, there are two such degrees of freedom. So, with respect to each of these we have to consider the equation of motion. When we consider it with respect to psi bar, we have no derivative term for psi bar. So, this is equal to 0. At when we consider dou L by dou psi bar, we have I gamma mu dou mu psi minus m psi, and equation of motion will tell you derivative or dou mu of the first line here plus or minus dou L by dou psi bar, second line is equal to 0. Since the first one is 0, we have I gamma mu dou mu psi minus m psi equal to 0. Indeed, we recognize this as the Dirac equation. So, this Lagrangian gives us the Dirac equation. What about the other degree of freedom psi. So, when we take derivative with respect to dou mu psi, we have I psi bar gamma mu and dou L by dou psi is equal to minus m psi bar. Together this will give you I dou mu psi bar gamma mu plus m psi bar equal to 0. Indeed, this is the conjugate equation corresponding to the above Dirac equation. So, we have the Dirac equation and the conjugate equation from this Lagrangian given here. Now, this it can therefore be considered as the Dirac Lagrangian if you want to name it. So, psi here is the field corresponding to the fermionic particles, and it is a function of the space time coordinates and momentum, okay, as we had written down earlier. All right. So, then let us go on to another Lagrangian, which I will write as minus 1 over 4 f mu nu the field tensor corresponding to the electromagnetic potential minus some current J mu A mu, potential A mu. F mu nu for us is equal to dou mu A nu minus dou nu A mu. So, if I expand the Lagrangian f mu nu, I have minus 1 over 4 dou mu A nu minus dou nu A mu contracted with dou mu A nu minus dou nu A mu minus J mu A mu. Remember also the Lagrangian density should not have any free index. So, all the indexes are summed over. So, then only you will have an invariant quantity. Lagrangian density is a Lorentz invariant quantity, Lorentz scalar. So, this is when I open the bracket dou mu A nu minus dou mu A nu dou nu A mu minus dou nu A mu, second term in the first bracket, times the first term in the second bracket, plus dou nu A mu dou nu A mu. Okay, so, that closes the bracket there, minus J mu A mu. So, this is equal to first term and the last term in the curly bracket. If you look at, they are the same, excepting that mu and nu are interchanged. Since they are dummy indices, if you interchange, nothing happens. So, I mean they are dummy indices. So, then they are the same terms. Similarly, you will recognize that the second term and the third term dou mu A nu dou nu A mu is minus dou nu A mu dou mu A nu are the same. For example, when you have dummy indices like this, you could change the upper and lower indices without changing anything. You will see that they are the same. So, I will leave that as a small exercise for you to raise everything and I recognize that they are the same. Essentially, this term that I will circle with a blue line. So, the one which I circle with a blue line are the same and adds up. Similarly, the other two, the other two which are left. Okay. So, the which I circled with red are also the same. So, they also add up. Together you have minus 1 over 2 dou mu a nu dou mu a nu minus dou mu a nu invert the switched a nu dou nu a mu minus j mu a mu. So, that is your Lagrangian density in terms of the potential, derivative of the potential as well. Now, let me take the derivative of the Lagrangian with respect to dou alpha a beta. So, I have taken alpha beta in order not to confuse with this mu's there in the Lagrangian. Okay. Let me take the first term here. Okay. So, the first term is going to give you. So, this is what we want to look at. So, let me take derivative with respect to dou alpha a beta of first term of the Lagrangian apart from minus 1 over 2 is dou mu a nu dou mu a nu. So, dou mu a nu dou mu a nu. So, this acts only on that and this acts only on that. This is equal to derivative with respect to dou alpha a beta. Again, let me write it as g rho mu g nu sigma or sigma nu dou rho a sigma. So, idea is to raise all the indices of dou mu and a mu, a nu, and you have dou mu a nu. Now, you can apply this, take the derivative here. So, we have rho mu dou sigma nu as a common factor, which is independent of space time or a coordinate the vector potential. So, we do not have this affected by the differentiation, but the other one first it will give you a delta of rho alpha and delta of sigma beta and dou mu a nu as it is, plus you have delta of mu alpha, delta of nu beta and dou rho a sigma. Which is equal to now delta rho alpha, when you will change the rho on the g rho mu to alpha, g alpha mu, g beta nu dou mu a nu plus similarly g alpha rho g sigma beta dou rho a sigma, which is essentially equal to dou alpha a beta, and the other one also give you dou alpha dou beta. So, this is twice this. So, first term here will give you twice dou alpha a beta, and do a similar analysis, and you will see that the second term will give you dou L over dou of dou alpha A beta as minus dou alpha dou beta A beta minus dou beta dou alpha A alpha. Okay. So, and this is the first part. Other term in the Lagrangian is j mu a mu with a minus sign. So, that will give you dou L over dou A alpha equal to minus j alpha. Okay, let me take the same j beta, and that will give you a j beta. So, together that will give you derivative of the first line with respect to alpha in the numerator of minus dou alpha A beta plus dou beta A alpha plus j beta is equal to 0. So, this is equal to essentially minus dou alpha f alpha beta plus j beta equal to 0, or dou alpha f alpha beta equal to j beta. You recognize this as the Maxwell's equations. Okay. So, therefore, the Lagrangian that we considered here leads to Maxwell's equation. All right. So, we have described three different Lagrangian. Okay. One, L is equal to 1 over 2 dou mu phi minus 1 over 2 m square phi square, and so that this gave us the Klein-Gordon equation, which is essentially box square plus m square acting on phi equal to 0. Then we looked at I psi bar gamma mu dou mu psi minus m psi bar psi, and that gave us the Dirac equation I gamma mu dou mu psi minus m psi equal to 0. And then we considered the Maxwell's Lagrangian f mu nu minus j mu a mu, and that gave Maxwell's equation dou mu f mu nu equal to j nu. Okay, so we have somewhat familiarized ourselves with the Lagrangian, and equations, and then we understand how we can write down the Lagrangian corresponding to the Dirac equation, Klein-Gordon equation, Maxwell's equation, which are the three familiar equations that we had discussed in the earlier this ones. So, the task that we have now next is how to write down the Lagrangian with interactions of the particles included. So, not just the free particle is not a very interesting thing, that will not tell us what the dynamics is. It tells us only how the free particle will propagate, that is fine, but if you want to understand the dynamics, how they behave under various different situations, especially under the basic forces, then we need to include the interaction in the theory. So, we will just now see how this interaction can be taken into account in this diagram.